Hey, Walter Sorrells back with more tips for the knife maker. Today, making a throwing knife on a CNC milling machine. Okay, so this is the third in a series of videos where I'm making an identical knife, a very simple throwing knife. The point is not that this is the perfect knife design or anything. The point is to show that there are a bunch of different ways of making very similar knives. All right, let's jump right on in. For today's project, we'll be using a piece of S30V, a high-performance stainless steel. As with all three blades in this series, the blade started its life as a CAD-CAM design. Now, unlike in the other two cases where the computer design was really just used as a rough template for a handmade blade, in this case, we'll take the CAD file straight to a CNC mill. But let's start with the design itself. I won't go through every single step, but the idea here was to use existing tooling and fixturing that I already use for my Tactics Armory knives to produce a very simple blade with a simple, easy to execute design. Now there's some nuancy aspects to various constraints and so on that I'll skip, but you'll get the basic idea by watching. I began by drawing two circles. There are also some dimensions and various construction lines that I tinkered with, and I won't bore you with all of that. Anyway, these two circles will ultimately be used for the clearance holes to anchor the steel to a pallet on my CNC machine using 1/4-20 screws. I know that I have two anchor points on the pallet that I'm going to be using at precisely 3-inch points, so I'll dimension them at 3 inches along a construction line. Next, I'll make an offset from that circle to produce the butt of the knife. A couple of 3-point arcs will serve to outline the handle. Additional arcs will complete the blade itself. For those of you who haven't worked with CNC or might be thinking about it, one of the most interesting challenges is that you're always thinking not only about the widget that you're making, but on a whole host of issues having to do with the way that it's made. How it'll be supported, how it'll be fixtured, what kinds and sizes of tools will be used, and so on. Now, because the material is relatively thin on a knife blade, tool chatter is a potentially big problem, meaning that when you run tools around the steel, if it's not properly supported, the material will tend to move and vibrate. This is terrible for tools, messes up tolerances, produces poor surface finish, and so on. It's just really bad. So I want a third anchor point out near the tip to prevent chatter in the blade section. The first two circles I've made will result in holes that are used to bolt the blade down to the pallet. But where do you put a third hole? You can't just drill right through the blade, right? Well, the answer is to make a tab. There are ways of generating tabs when you start doing the CAM, that is the manufacturing part of this process. But to me, the methods that are built into Fusion 360 are a little bit of a pain to use, and it's not as easy to locate precisely where that tab is going to be as it is if I just design them right into the part from the very beginning. So by just designing the tab into the knife and then grinding it away later, I can control where that tab is down to the 1/1000th of an inch and then ditch it once it's served its purpose. Being able to locate it with a great deal of precision is important because, as I said earlier, I'm using an existing fixture that's used for one of my production knives. So the holes are already drilled and I have to adapt my knife to those holes instead of working it the other way around. See, for a one-off blade, I don't want to have to reinvent the wheel and build a bunch of time-consuming fixtures. So like I said, I've designed the tab right into the part, using construction lines to dimension the bolt hole to the 1/1000th of an inch so that it lies exactly on the knife where it'll be on the pallet that I'm going to screw it down to on the CNC machine. Now this fixturing method, where you're basically locating everything based on bolts, wouldn't be precise and repeatable enough for a lot of applications. The reason for this is that you'll have minor deviations in the position of the blade caused by little wiggles between the hole and the screw. But in practice, the amount of wiggle is only in the range of a couple thousandths of an inch. So for this particular application, it works just fine. If we wanted more precision, we could use high precision locating pins and things of that nature, but that's really overkill for this dopey little knife. Alright, now we've moved on to the CAM or computer-aided manufacturing part of this process. This is where the actual tool paths, literally every move made by each cutting tool involved in making this blade, will be detailed. In this case, we're kind of Frankensteining this blade from an existing setup, so we won't have to detail the way the holes are drilled in the pallet that we're going to be screwing it to. We'll jump right to profiling the blade. This is a pretty simple process. We'll import the design into the pallet setup, then use joints to align it to the pre-existing bolt holes. Once that setup's done, we'll use a 3/8 inch end mill to rough out the profile. Then a 1/4 inch end mill will take a final cleanup pass around the profile of the blade. I could do lots more things at this point if I wanted. I could chamfer the edges and even mill bevels on the blade itself. But that would create fixturing problems that would take literally days to solve. I love you guys, but I'm not burning 2 or 3 days of work on that. Instead, I'll just bevel the blades on the grinder and save myself a ton of time. Anyway, the next process is to generate G-code. For guys who don't do CNC, this is the set of instructions that will tell the milling machine exactly which cuts the blade makes. I do that by posting the file. That code is then uploaded to the controller of the CNC machine, and we're ready to start cutting steel. Our first op is drilling, which I do on this little fixture plate. I didn't show this part earlier because I'm actually using a drilling operation from a totally different knife. Anyway, we hit the go button and start drilling. Now, of course, I realized later that I made a mistake in not tinkering with the hole drilling operation from the other knife. It ended up putting the holes off center on the blade. It's not a functional issue, but kind of bush league looking. But hey, this is basically a one-off prototype-y kind of thing, and the whole nature of prototypes is that they never come out perfect. That's my story, and I'm sticking to it. In all seriousness, obviously, if this were something that I was making a bunch of copies of or that I was going to be selling, I would sort that out and it'd be quite easy to do, but we're stuck with it now. Alright, so next we'll mill out the profile of the knife. Now this is a high carbon vanadium chrome steel, very nasty on cutting tools. For folks who've mostly done milling on aluminum or even on mild steel or high carbon steel, believe you me, this ain't that. You have to be pretty mellow about how hard you push this stuff, especially with a fairly small system like my Tormach. That said, we can cut stainless tool steel just fine on this system. You just can't go too buck wild on it. For you CNC geeks, I'm running an aluminum titanium nitride coated Lakeshore Carbide 4-flute cutter here. I'm running around a 0.05 inch step over, about 1900 RPM, feeding at 7 inches per minute. If you haven't used Al-10 coated tools, they're intended to be run hot. They achieve maximum lubricity, which is a fancy word for slipperiness, when run at about 800 degrees Fahrenheit, so you don't want to use coolant on them when cutting steel. I'll just be blowing a little air to clear the chips. When I run a brand new cutter with this recipe, I tend to get gold colored chips, but as the cutters wear in, which they do pretty darn quickly with this kind of steel, the chips start going blue and then purple and then gray at those same speeds and feeds. In theory, this means the chip is going from around 400 Fahrenheit when it first starts cutting to around 6 or 7 or 800 with those darker colors. We're done now, and here's the blank, ready for the bevels to be ground. So, it's on to the grinder. If you want to see more detail about this part of the process, we'll have a link in the cards here to video number 2 in this series, which goes into more detail about the grinding process. A lot of folks are going to have watched that video too, so I'm not going to repeat it. So all done, and here we are ready for heat treat. We'll wrap the blade in a pouch of heat treating foil, which will protect the blade from oxygen during heat treating. If you expose the blade to oxygen for the extended period of time that the blade's sitting there in the heat treating oven, it will not only develop scale, which is a giant pain to clean off, but more importantly, it also leaches carbon out of the blade, a process known as decarburization, which can soften the outer portion of the steel and especially the cutting edge, leading to lower performance. So, it's into the heat treating oven for a 30-minute soak at 1900 degrees. There are a lot of different ways of quenching a stainless steel blade, but in this case, we'll use what's known as a plate quench, smashing the blade between a couple of aluminum plates. This is an air hardening steel, so you can just take it out and let it cool in still air or cool in front of a fan or something, and it'll harden nicely. But the advantage of plate quenching is that you can reduce the likelihood of the part warping. On one of my production knives, the process is a little more complicated than I'm showing here, but for a beater like this works just great. After cooling to the point where you can touch it, the knife goes back into the heat treating oven for 2 cycles of 600 degrees each. This will result in a knife that's fairly hard, but not too brittle. A little cleanup on the grinder, and we're ready to join the carnival. Alright, so I just want to say again, I hope you get a chance to watch all 3 of the videos. The whole point of this is, here's an extremely simple design that you can execute in a multitude of different ways and, still result in a similar kind of knife. Everybody comes at this with different equipment, different skill sets, and so on. And the point of these 3 videos is to say, hey, look, here's kind of a smorgasbord of approaches that you can use to make a knife and pick the one that works best for you. Thanks for watching, guys. If you feel like you got something out of this video, don't forget to subscribe. Also, click on the link to Patreon for a great way to give back to the channel. Plus, check me out on Instagram, Facebook, Twitter. Links in the description. If you want something sharp and pointy, maybe a gift for yourself or one of the cooler people in your life, check out my Tactics Armory website and pick up one of our tactical or outdoor knives. And finally, if you want to learn to make Hamones or Japanese swords, check out WalterSorrellsBlades.com, where you can find videos about how I make Hamones, as well as forging, mounting, polishing, and fittings for Japanese swords. Thanks, and see you soon.